Kaposi, Ambrus. So that it's on the internal parametricity without an interval. Please.
Yeah, thank you. So this is joint work with Thorsten from Nottingham, Yorgo Chamoun, he was a student intern from École Polytechnique, and Mike Shulman from San Diego. And this talk will be about identity type in type theory, and we will get to parametricity very soon. So identity type or equality type can be used to express the equality of two different things. So for example, equality of 1 plus 1 and 2. So how do you prove this in type theory? This is the identity type here on the right-hand side, and the left-hand side we want to write the term. Oh, sorry. The connection is... maybe it's frozen, so replug and unplug, no?
That screen is frozen for some reason.
Yeah, that is frozen, but here it's fine. Shall I try unplug, replug? So it's some sense of fakeness.
Yeah,
in the meantime, we can kind of get people more in the middle so there's edge seats because we're trying to fill up again. So we're all friends here. Sit next to each other.
Yep. Yeah, okay.
Yeah, we should be looking up. Yep. Okay.
Right, can I continue or restart? Yeah, so this is the identity type which expresses equality of the two natural numbers. Here it's natural numbers of 1 plus 1 and 2. So, and on the left-hand side of the column, I need to write a term or a proof of this fact. So how do I prove this? Plus is a function which computes. We are in type theory, or a computer program which computes to 2. So in fact, I only need to give a term of type ID 2. And if I know that my identity type is reflexive, so I have this reflexivity term at 2 will prove for me that 1 plus 1 is equal to 2. Okay, so how do I prove something more complicated? I have a variable x, and now I need to prove that x plus 0 is equal to x. So here this doesn't compute because I happen to define addition by recursion on the first argument. So it's piano natural numbers. So I know that if I add 0 to a number, it stays the same. And in the successor case, there's a recursion happening, but if the variable here is the first argument, then it doesn't reduce, so this is a stock term, so then I need to use induction or something more fancy to prove this theorem. And in general, so the identity type for every type A, I have the identity type A, which is a double indexed family of types over ID of A, so you can take, this is like the in the classical way of representing, it's a homogeneous binary relation, and we represent it with this characteristic function here. And if I have a term of type A, I also know that this type, I have reflexivity of A, which is a witness of the identity type, and then I have some more rules. So what are these more rules? How do I specify the other rules of type theory? So one, the way by Per-Martin-Löf is very simple, it's a very nice way. It's saying that it's an inductive type generated by the reflexivity constructor, and then this gives a notion of eliminator, which is the J. So one problem with this is that this only works well for identity of inductive types and not for co-inductive ones. So in particular, for function space, we cannot prove this in Martin-Löf type theory, that these two functions, x plus 0, which add 0 to an input natural number or just the identity function are equal, so we need function extensionality or some extra principle, or a different definition of identity type, such as the one in cubical type theory, where there's a formal interval added to the syntax. This I is the formal interval, which has two formal endpoints, 0 and 1. And then you can say that two elements A and B are identical or equal if there's a map from the interval to A, okay, such that that map starts at, when it starts at its starting point, it maps the starting point 0 to A, and it maps the ending point, the endpoint 1 to B. And with this, you can actually prove the previous one, so function extensionality becomes provable. Then there's another way, observational type theory. So here we define the identity type by computation. So for example, for identity type of natural numbers is given by these computation rules. So equality of 0 and 0, it computes to the unit type, so or top, or it's true all the time. If it's a successor, the diagonal case, then we recurse. So successor of m is equal to successor of n if m is equal to n. And in the non-diagonal case, we return the empty type, right? So similarly for product types, identity of A times B is an identity in A and an identity in B, and this is also a computation rule. Or for the function space, keep in mind this example, I have that F0 and F1 are equal if I have two equal inputs, A0 and A1, and this F0 and F1 map them to equal output. So this is also a recursive definition, similar in the fashion that we saw for the product type. Okay, and then this talk will be a step towards higher observational type theory, which is not a well-defined type theory yet, but it's work in progress. And here we also define the identity type by computation, just as in observational type theory. But we have this higher rule that the identity for the universe of types, so when are two types A and B identical, we say that they are identical if there's an equivalence between them. So this is a definitional version of Vygotsky's univalence axiom, which assumes the weaker thing that the identity type is equivalent to equivalence. Here we want a definitional equality. So the promises of higher observational type theory, if it delivers, it will deliver an explainable, simple type theory with identity type and univalence. So it would be an implementation of homotopy type theory, which doesn't have interval, it doesn't have built-in geometry, only low-dimensional operations. The identity type or geometry would be emergent, just as there is geometry already built in Per-Martin-Löf's type theory, because you can iterate the identity type and get cubes or simplices that way. It will have computational univalence, so this should be a computation rule, unlike in cubical type theory, which is where it only holds up to equivalence. And it should be a simple extension of Martin-Löf type theory with some new rules. So the current techniques of implementing type theory in an efficient way should scale to that, and hopefully we get an efficient implementation. But this paper is just a baby version of higher observational type theory. So what are the aspects of babiness? So the first babiness is that there's no identity type, okay? There's only logical relation, which can be seen. Logical relation is like an identity type, which is reflexive. It's a congruence, so if A is equal to B, then FA is equal to FB for any F, so everything respects identity, but it's not symmetric, it's not transitive, there's no Leibniz rule, there's no general J eliminator for it. And it can also be seen as a kind of abstraction principle. So just as Vygotsky's univalence says that everything preserves equivalences. Whatever you write in type theory, you cannot distinguish equivalent things. And Reynolds parametricity says a bit different. It says that everything preserves relations. So these two principles, neither of them is more general than the other, but they can, sometime in the next talk, we will hear about how they can play together at the same time in certain type theories. But it's also from defining a type theory with internal parametricity is slightly simpler, because parametricity parametricity is everything but equality except the transport rule. So we don't have to implement the transport rule. That's why this is the first babiness that we want. Then the next babiness is that in contrast to what I promised at the previous slides, not everything is computational. So, for example, identity type, the rule for identity type, that identity type of A R O B is like identities of A are mapped into identities of B. This is not a definitional equality or a computation rule only up to isomorphism, but this should be easy to fix. Now, the one which is, it seems it's not really possible to fix is that the next one, which I said we would have computational univalence or definitional univalence. So the identity type of types A and B, here it should correspond to relation space instead of equivalences. That's also not a computation rule, and it's not even an isomorphism, it's a section retraction pair. So in our theory, what we have, if we start with a relation, we turn it into an element of the identity type. By the way, this is usually called breach type instead of identity type for parametricity, but for simplicity, I just call it identity. And then you go back, you get a definitionally equal relation, but not the other way, okay? And then finally, we don't even have logical relation, okay? We only have logical span, so instead of a relation, we have a span. So instead of IDA, I have a type for all A, together with two maps into A, 0 and 1, which give you the two endpoints. So this is like the Grothendieck correspondence, fibers and indexed, and we are staying on the fiber side. I will say you some reasons for this, but even in this setting, you can, in this like through the glass looking setting, you can see, or you can imagine how great it will be once we see higher observational type theory face to face. Okay, so now I want to say some technical things. So our semantics is Bézem-Kocan-Huber cubes, cubical sets. So this was the first model of univalence, but they never built a cubical type theory on top of the cubical sets. These are the most natural, or they correspond to the classical cubical sets or classical simplicial sets. They also have a simplicial version. But because if you build the identity type using the interval based on these sets, then the interval becomes substructural, so very weird rules for substitution, and it's difficult. So this is what the category looks like. These are the dimensions, 0, 1, 2, 3. These are lines, squares, cubes, and so on. And then you have lots of maps between them. So for example, for a line, you can get the two endpoints using these maps. So there's a concise presentation of this category by this, which is generated by this two category, okay? So it's a two category with one object star, which I drew twice, one morphism sock, which goes from this object to itself. Then you have four two morphisms or two cells, this R, 1 and 0, and this here I just composed the successor with each other, and then there are 5 equations which govern this, and then the nice thing is that this diagram generates all of this category. So now I labeled some of the arrows to show how they are generated from this. I won't get into the details, but this is the diagram that we keep in mind, okay? And this generates our syntax. So our syntax, we don't invent beautiful new syntax out from the top of our head. We just extract it from the semantics. So how do we do that? So this cube category induces structure on presheaves or families on these objects and morphisms of the cube category. So in particular, we have this presheave model of type theory, and we have a morphism of models, sock star, which is precomposition with the sock, which I just called for all, which is exactly the same for all that I showed you before when I said I have spans instead of relations, okay? And so I have a morphism of models together with these natural transformations, okay? And then I just call that a syntax, okay? So this structure is my syntax. I have type theory, a model, and then I extend it with whatever I can read of this diagram. So for example, because this for all is a morphism, for every context I get a new context, which is the for all version. For every substitution I get a for all. So here for every type, I get its identity type. So for all of A is a heterogeneous identity type because it depends on for all of a context, not in the same context, okay? And then I have these maps. So for example, from the identity type of context, I can go to the endpoints. And from these, okay, so one of the technical comments is that for me, I thought that this type theory is not, you cannot do this, because what are the rules for symmetry? Like, how do I specify how symmetry computes? And the point was, you don't have to specify it. It's just a natural transformation, and that's all. And that's enough, and everything is derivable from that. Okay, but this type theory is still weird because it has an operation on context. You don't want this. So now you have, now you use logical framework, two-level type theory. It's also called higher order abstract syntax, this idea. So now I will generate a new syntax from the exact same diagram, but now it's not from pre-sheaf model to pre-sheaf model for all, but it goes from the standard model, which is internal to pre-sheaves over pre-sheaves, which I won't explain here, but the syntax that you get is exactly determined by this again, and this is a nice structural syntax, and just very quickly, so for every type, I have for all of A, which is its homogeneous identity type. Only one more slide left. And I have a up or congruence operation, and I have a heterogeneous identity type, which is indexed over the homogeneous identity type and the heterogeneous version of up, and then the same maps and symmetry, and then 5 more equations. Yeah, and then I have some more equations for each type former, which describe how they behave. But this is the essence of the syntax, and it's very like principled. So in summary, we defined in this paper type theory with internal parametricity. In the paper, there are some usual applications of internal parametricity, like the polymorphic identity function example, Church-encoded natural number support induction. And this is the first structural type theory for BCH cubes. So the substitution behaves as it, and variables are as usual. Geometry is emergent rather than built-in, so it's simple, and we prove canonicity. And there is some future work. Thank you.
All right, thanks for the talk, and we are taking questions.
Hi, that was a very energetic talk. Thank you. So I wanted to ask you. So when you have this these kinds of proof-relevant relations or spans, do you get anything like the identity extension property from the relational version, or does it come out differently?
So I never understood this identity extension property, and I read some claims that these kind of theories with internal parametricity, they don't satisfy it, but I think they do, because we are able to prove that Church-encoded natural numbers have induction. So I think we do have, but I don't understand what it is. Yeah. Yeah.
Maybe we can.
Yeah, I'd be interested.
Okay, because we started really late, let's take 2 more quick questions. One more?
There's an online question.
Oh,
So what's the intuition for the notation for all? Yeah.
So I got it from Guillaume Moulin's thesis, who also developed some theories with internal parametricity. But yeah, I don't know. Maybe it should be called EQ, or it's basically the total space of bridge, or like it's a bridge with its parts where it sticks to the side of the river, you know. So what do you call this? So all of the bridge. Yeah, but
okay, there's one.
So the fact that this is a structural theory suggests that it might be easy to implement in real implementation. So do you agree, or do you see obstacles to implementation that
Yeah, so you have more neutral terms. So I think the techniques by Connor, McBride, and others on new equations for neutral terms, those are the kind of techniques that you need to employ, but it should be easy. And compared to cubical type theory, you have where, for example, you need to have substitutions in values, substitutions by interval variables, so that we don't have here. Yeah, so it should be simpler.
All right, so let's thank the speaker again.